So let's start off with module 5, which is pseudo random sequence generators along with stream ciphers. And this module uses text 2 as your reference. So till now, the first 4 modules which we discussed is from text 1 only, that is William Starling's 6th edition. This is text 2, which is Bruce Schneer. Both the textbooks I have posted in the classroom initially itself. So for this module, you have to completely refer text 2. This text 2 is not so easy to read, and there is no much of detail, especially as we go further. But you can understand whatever is the minimum required. And as we proceed further, the things which we talk of, the practical implementation of these stream ciphers, it will be asked for short notes basically, explanation or short notes. Okay. So you need to write what is mainly there in the textbook, which is not much, but some additional things you need to learn. If you have to understand the working, you will have to learn things additionally more than what is there in the textbook. So just remember that. Please refer Bruce Schneer. So this textbook is Let's move on. So what do you mean by true randomness? How do you say a given sequence exhibits true randomness? So we say there is true randomness only if it is naturally generated as a random event. Let's say, for example, the recording of ticks in a Geiger counter. Remember, we use a Geiger counter for measurements with radioactive elements, even with respect to earthquake measurements. So whatever ticks we measure from that is something which is truly random. It's not something that a human being has simulated in the lab. So anything which occurs on its own naturally and which seems random, where you don't have any control on the count or the timing or anything, that is true randomness. But what is pseudo random then? We need this randomness. It's a very useful phenomena in many of our electronic, whether it is communication systems or cryptography. What is this pseudo randomness? As I told you, it is something which gives you the appearance of randomness, but it won't be actually random, for the simple reason that it is generated by a human being using some experiment in the lab. Okay, so whenever we generate a random number, you can always expect that it will repeat itself after some interval of time, and that interval of time or the time period after which the number repeats itself can be made very, very large. Then it will give you the appearance of true randomness. So when will a pseudo random sequence look like it is truly random? When the length of the sequence or the time period of the sequence after which it repeats itself is huge. You can't comprehend how big it is, so that you will not see the repeatability. Okay, so you will never get to know that it is actually a repeating sequence, but you can see that it is repeating theoretically. It will repeat itself because you know how you are generating that random sequence. But to see that repetition, that period will repeat itself, say after 2 to the power of 20, let's say numbers, or after 2 to the power of 50 numbers. So you generate a very huge, large time period after which the numbers will repeat themselves. Then the sequence which you have generated will appear like a truly random sequence, and hence we call it as a pseudo random sequence. Pseudo means, what is pseudo? What does the word pseudo mean?
False. False.
Pseudo means false. So actually it is falsely random, but because you are going to generate a sequence which appears like a truly random sequence, we call it as a pseudo random sequence. And that repeatability will never come into observation if you generate a random sequence with a very large time period. Okay, so just remember that. Numbers calculated by a computer through some deterministic process, by definition, cannot be truly random, it will be pseudo random. That's what I told. Only natural processes like a radioactive element generating ticks in the measuring Geiger counter, earthquake measurement device, or all those things will be naturally random. But something which is generated by humans using a deterministic process will be pseudo random in nature. But you never get to know the falseness of the random number generator if you do it properly. If you generate a long time period between the repeatable sequences, then you can give the appearance of true randomness. So, given the knowledge of the algorithm used to create the numbers and its internal state, we call the initial state as the seed value. So, the internal state, or let me say, it is the initial state. Okay, so that initial state is also known as the seed value with which we begin the random number generation. Okay, so if we know that, if I know what is the seed value and if I know what is that deterministic algorithm which is used to generate the random numbers, then I'll be able to predict all the subsequent numbers which will be coming out of the random number generator. You have seen it happening in the labs also. When you use certain commands in the C lab, you saw that rand function, it will generate a predictable random sequence. If you use IRAND, if you use a different function, maybe not so predictable, but it is also predictable, but it will be predictable after a large interval of numbers, a large period. That's what we mean. Okay, so by calling to the program subsequently, I'll be able to predict all the remaining numbers. All these numbers are called pseudo random numbers. See, computer generated random numbers are properly referred to as pseudo random numbers and pseudo random sequences of such numbers. So here you can see a simple cartoon which where this is demonstrating the random number generator, and the random number generator is simply predicting 9999. You can see that the main problem with random number generators is we don't know if it is truly random. All these nines can be random or it need not be random. Anyway, so moving on, let's see what are stream ciphers. So what are these stream ciphers? We know till now. Do you remember what are stream ciphers? Anybody? Block cipher and stream cipher. You remember the difference? When you work on data bit by bit or byte by byte, it is called a stream cipher. When you work on data as a group of bits or a block of bits, it is a block cipher. Remember our symmetric cipher algorithms like AES and DES are preferably block ciphers, whereas the classical cryptographic algorithms which we have used are generally stream ciphers. Usually, even public key cryptographic algorithms are normally stream ciphers rather than block ciphers. So please remember the basic definition of a stream cipher. So whenever you do the encryption bitwise or bytewise, then it is called a stream cipher. We know till now the one-time pad is the only theoretically secure cipher with a truly random key sequence used. But we saw this is not used practically because how do I transmit such large quantities of secure key? You are going to use a truly random number generator to generate the key. But how do you share that key with the receiver? How do you transmit that key securely? That's the big issue with usage of one-time pad. Okay, that's why it's not used commonly. So a more practical alternative is a stream cipher, which we are going to study. Here we are going to generate a pseudo random key stream from a starting value known as the seed value. A real key which is much shorter than the full key stream will be added to the message. So when we transmit the message, we are also going to transmit a real key. That real key is not the actual key, but it may represent the seed value. And the algorithm is agreed upon before itself between the transmitter and receiver, so that using that seed value, the receiver can use his own pseudo-random number generator and generate the keys. Okay, so we try to make the set of all possible seeds, real keys, everything so large that brute force or exhaustive search will not be possible in practice. Okay, so even if I use brute force, I won't be able to find the key because we are going to make the complete group of the key values. I told you real key is a shorter version of the actual key. Say I'm using a 1024-bit actual key. I'm going to generate a real key of 112 bits or something like that, and I'll append it with the message and send. So that real key represents the initial seed. The receiver will use that initial seed value or the starting value in his own random number generator, which will be running the same algorithm as in the transmitter. Okay, so transmitter has an algorithm, the same algorithm will be in the receiver also. And if the same seed is used by both, they will generate the same random number sequences. That's the idea behind stream ciphers. Okay, so brute force will become impossible when we make the key space very large. The seed values, key space, everything is made large. And we'll also try to eliminate any shortcuts of finding this key. So let us first discuss what are linear congruential generators. In short, we call them as LCGs, linear congruential generators or LCGs. So what are these LCGs? These are the most common generators used to generate pseudo-random numbers, and they were the initially designed ones. So though they are not very efficient, they give us the basic idea of how random number generators should look. Remember, random number generators is compulsory for us in cryptography and also in communication. So we won't be doing efficient cryptography or efficient communication. These are just two major applications. Along with that, we have many other applications which are there. See, I'm telling you again, I don't know why you people are entering the USNs. I'm deleting all these USNs. It won't be considered. If you are planning to enter your USN and leave the class, you can do it, but I'll consider the USNs which is entered at the particular time when I'm going to ask you to enter. So stop entering it. Here, as I was telling you, the most basic type of random number generators are called linear congruential generators. And they are defined using this equation, or more commonly, we'll write it as xn is equal to a into xn minus 1 plus b mod m. In this case, xn minus 1 represents the previous number generated. So this is the previous number. This is the present number to be generated. A and B, A is a multiplier. So A is the multiplication value, the multiplier, and B is the increment. As you can see, it is plus B. And M is the modulo value. Okay. The same, you can use the equation either in this form or in this form. We consider this form more commonly. That is, xn is equal to a xn minus 1 plus b. So both mean one and the same. Okay. And how do we normally represent this as an LCG? I'll call this as LCG with the multiplier a first, then the increment. So this increment can be b or c. So whether I specify, whatever I specify second, it is the increment. So plus b or plus c, whatever. Then I'll have the modulo value. And finally, I'm going to specify the seed value or the initial value. All of you please make a note of this. So how are we going to represent the LCGs? The multiplier, increment, modulo value, and the seed value. This is how we are going to represent the LCGs. Okay. So the next random integer is generated using previous random integer and the constants a and b along with the integer modulus. To get started, we always need a seed value x0, which should be defined by some means. So we refer to the LCG as shown. The appearance of randomness is provided by performing mod arithmetic or what? Remaindering, or we find the remainder after computing the given modulus. We call that as residue arithmetic also. Okay. So because we are using modulo, we get the appearance of randomness here. Also, remember that the next random number always depends on its previous value, which may be the present random number. If xn is the present, xn plus 1 will be the next. So it always, the next one depends on the present one depends on the previous. This is how we do the random number generators. So this is an important characteristic of linear congruential generators with minimum storage requirements. But one major problem with LCGs is it puts some restrictions on the period. So the length, time period means, or the period or the length, if I say, please understand, it is the what? Total number of values until which the residues will start repeating, or until which the numbers start repeating. Okay. So how many random values I'm going to get before it starts repeating itself? That is known as the length or the time period of the generator. Please remember that. So continuing, as I told you, LCGs are pseudo-random sequence generators, which can also be written like this. I already told you. xn is the nth number in the sequence, xn minus 1 is the previous number, a is the multiplier, b is the increment, m is the modulus, x naught is the key or seed value. Now, the generator has a period which is which cannot be greater than m. Please remember, if I use a modulo m value, I can never have the period of the generator to be greater than m. Okay? And if we choose the constants a, b and the modulo value m correctly, then we can generate a maximal period generator or a maximal length generator. So what is this maximal period or maximal length generator? The highest period can be m, or usually we say it is m or m minus 1. If I am able to generate a pseudo-random sequence generator with repeatability after m or m minus 1 values, then it is called a maximal length LCG. Okay. So, whenever xn is determined, we also need to find a corresponding real number corresponding to that xn. We call that as Rn. So how do we find this real number? Again, there are two options. Either you take xn and divide it with the m value, floating point equivalent of m value, or you divide it with m minus 1 value. So depending on the situation, generally we consider this first one, xn divided by m. Okay, very often the period will be m or whatever. If I have a modulo value m, I'll find this real number as xn divided by m. So whenever we divide with m, the values of this real number will be somewhere between 0 and 1. Remember, I can never get a value greater than 1. And normally we want uniformity in the pattern of the random numbers generated. So the random numbers generated should be uniformly distributed. In that case, Rn should be very close to the average value of 0.5. Remember, I am distributing the numbers between 0 and 1, which means, say for example, between 0 to 0.25, I have, say for example, 10 numbers. Then between 0.25 to 0.5, I should have 10 numbers. 0.5 to 0.75, I should have 10 numbers. And 0.75 to 1, I should have 10 numbers. So if there are totally 40 random numbers generated by the sequence, I should have 10 distributed in each of the quarters. This we call as uniformity or uniform distribution. Say for example, I have 5 here, 15 here, another 15 here and 5 here. Then there is no uniformity in the distribution of random numbers. So please remember, the more uniform the distribution is, the better. So it is more close to randomness. If the distribution is not as uniform, then it is not very close to random. So what is the midpoint of these two? It is 0.5. That's why we need the total computation of Rn to be as close as possible to 0.5. Remember that. Now let's take some example LCGs. Let's take the first one. See, it is written as LCG 5, 1, 16, 1. So remember, this is A, this is B or C, whatever we want, we can call it as increment, multiplier. This is the modulo and this is the seed, x naught. So how do you define the equation? I can say xn is equal to 5 times xn minus 1 plus 1, right? So this will be the defining equation. Now based on this, you try to find the various numbers. What should I put for xn minus 1 in the first place? What should I put for xn minus 1? Yes? It is the initial seed value. X naught, the seed value is given, right? So you start off by considering, in the first place, you write x1 will be 5 times x naught plus 1. And what was x naught given as? 1. So it will be 5 plus 1, 6. That is x1. What will x2 be? X2 will be 5 times x1 plus 1. So always the next number depends on the previous number. So this is 5 into 6 plus 1. And remember, there is always a mod 16. Since 6 is less than mod 16, this will remain as 6. But here I am going to get 31. Is that right? 31 mod 16, how much will that be?
15.
15. Likewise, you find the next number. What's the next number in the sequence? X3 will be 5 times X2 plus 1. So 5 into 15 plus 1. This will be 76. Tell me how much is 76 mod 16?
12.
12, ma'am.
12. So likewise, you can find the numbers. You will see you will get non-repeatable numbers which are how many in length. So if I start with the initial seed position here 1, you see we have written all the random numbers as points on a circle. So after 1 we have the next number 6, then 15, then 12. And likewise, if I continue, x4 will be 13, so on. You will get all different residues until you get 0. And once you come back here, it will start repeating. So you can see that it is going to, in every quarter, I have approximately how many? If I consider, I have approximately 4 random numbers in every quarter, right? So totally I have
16 numbers.
16 values generated. I told you this is equal to your M. So what can I call this LCG as? What will be the name given?
Maximal period generator.
Maximal length or maximal period LCG or maximal period random number generator, pseudo random number generator. Okay, so this is an example of LCG. So what do you observe here? The period is 16, which is exactly equal to the modulus M. That's what I told you. So for M is equal to 16, this is of the longest possible period. And another thing is it generates the random numbers uniformly. That means it's completely filling the space of integers between 0 to 15. You see, when I put it along a circle, it has every quadrant or every quarter has equal number of random numbers. So it is uniformly generating all the random numbers. Okay. Here, the sequence will exhibit uniform distribution of even and odd numbers. You can see in this pattern here. You see, if 1 is an odd number, the next is even, again odd, even, 15, 12, odd, even. So it's giving a uniform distribution of odd and even numbers alternatively. It's also apparent that it is serially correlated. which means there's always a relationship between. So I can say if one is odd, I can clearly predict the next one will be an even number. And given the set of even numbers which is already occurred, I can say this should be one among the remaining. So I can say few things are predictable or there is a correlation between the successive numbers. So clearly it is lacking true randomness or sufficient randomness. So usually we don't use this as a random number generator for such a small value of n. Okay. If the time period is so small, generally we don't consider. So the real numbers generated from the integer sequence are normally sufficiently random in higher order bits. So if I represent these 16 numbers as a 4-bit pattern, if I consider the MSB, there we can see it is little more random than the LSB. You see here, this is how we write the table. So when we write the table of these LCGs, just a second. Yeah. We normally list the n value, then the random integer xn, which is being generated, its binary representation. You can see the appearance of randomness can be seen somewhere in the MSB bit. This bit, the 4th bit here or the leftmost bit, and not in the other 3. Because the rightmost bit, if I consider, I know if the present is a 1, the next will surely be a 0. If the present value is a 0, the next bit will be a 1. Similarly, the next column states 2 ones, 2 zeros. Then 2 ones, 2 zeros. Coming to the most significant bit, usually we can't predict so easily because I have 2 zeros, 3 ones, then again 1 0, 4 ones, 3 zeros. So here the predictability is lost. So if you want to consider this as a random number generator, I have to use the MSB bit position as a stream cipher. So if I just consider this MSB bit position, here I can see there is some randomness when compared to the other bit positions, and then it can be used as a pseudo random number generator. Okay. And next column is about computation of the random number Rn. I told you, how are we going to find that random number Rn? Rn is defined as xn divided by m. In this case, xn is 1. So 1 divided by 16, the value is 0.0625. In the next case, it is 6. So for this Rn will be 6 by 16, which turns out to be 0.3750. So this is how you are going to find the value of the random real number Rn. Okay, this is not xn, this is Rn. And in the end, I am computing the average value of this Rn. So I have determined Rn for each of the xn values. The random number integers xn for every xn. For every xn, I am going to compute this Rn. So 15 by 16.9375, then 12 by 16.75, so on. And in the end, when I take an average, I am going to get 0.4688. What should be the ideal value of Rn? Coming back to LCGs. As I was telling you, we compute the real number Rn using this. What should be the ideal value of Rn? Remember, Rn is a number which will be lying between 0 to 1. So the ideal value of Rn should be 0.5, which means I'm getting this Rn average of all these Rns generated to be around 0.6, 0.46, which is slightly less than 0.5. So it is not so very close. Okay. And I can also compute the variance of all these values, standard deviation or variance of each of these values, which turns out to be 0.83. And the ideal value of variance should be somewhere around 1 by 12. Okay. And you'll get something close to that. So what is the inference next? Because each random number results from the previous integer alone, selecting any initial seed from 0 to 15 would cyclically shift the above sequence. So it will still generate the above sequence with 16 numbers, but it will be simply shifting the value. Instead of taking x0 as 1, say I'll start with x0 as 6. So 6 will be the starting value, then it will be 15, then 12, so on. 1 will come later. So I can use any of the numbers in the sequence as the initial seed value. Okay. All that a different choice of initial seed does here is shift the starting point in the sequence. So A, the multiplier, the increment, B or C, and modulus will already determine the sequence, what should be the next value and all that. So only the starting point will be changed. Again, as I was telling you, we note that the average of the real numbers is 0.4688 and the variance is 0.0830. The ideal values of what? The average, mean, we say mean or average should be half, 0.5, and the variance ideal value should be around 1 by 12 for this. This, if you try to compute, this 0.46 is slightly less than half and 0.083 is slightly less than 1 by 12. Okay. So they are approaching the ideal values, but they are not exactly equal. The more close they are to the ideal values of mean and variance, the better the random number generator, the better the appearance of randomness which it is going to give. Okay. So some random number generators which have long periods will have their mean of Rn as almost 0.5 and the variance as almost 1 by 12. So can you see another example of LCG here? This is special in the fact that the increment is 0. So what will be the equation? Here xn will be 5 times xn minus 1 plus 0 mod 16. So if you substitute x0 as 1 here, the seed value, if I put it as 1, I'll get the numbers. So the seed value is the first number 1, x0. Then I'll get x1 as 5 into 1, which is 5. Then I'll get x2 as 5 5s 25 mod 16, which will be 9. And x3 as 5 9s 45 mod 16, which will be 13. So after that, if I put 13 as the previous value, 13 5s 65 mod 16, which will again generate 1. So 16 4 64. If I do 65 mod 16, I'll get 1. So you see just 4 numbers are generated in this sequence. So can I call this as a maximal length generator? Can this LCG be a maximal length generator or not?
No, ma'am.
Surely it can't be a maximal length generator because here M value is 16, but I'm getting a time period, a period of just 4. After 3 it is repetitive, right? So this is surely not a maximal length generator. For this generator, if I try to substitute the binary equivalent values and the corresponding real number Rn. So the corresponding real number Rn, if I try to substitute, again 1 by 16 is 0.0625. Then 5 by 16, I'll get this. This is 9 by 16 and this is 13 by 16. Average value you can see turns out to be much lesser than the ideal value of 0.5, and even the variance is much lesser than the ideal value of 1 by 12. Okay, so surely the deviation from randomness is higher here. So if I look at these sequences, I can't consider any of these bit positions. The last bit position is all 1, then it's all zeros, then 0, 1, 0, 1, then 2 zeros, 2 ones. Nothing looks random here. If I look at each of the bit positions here, whether it is the LSB position, the position next to LSB, nothing gives you an appearance of randomness because it is repetitive. In LSB bit position, it's always ones. In the position next to that, it's always zeros. Next to that, it's alternate zeros and ones. And next to that, it's 2 zeros, 2 ones. So that goes on repeating. There is no randomness possible here. Okay. So lower order bits are not random. Sequence is surely correlated. All successive integers differ by 4 from their predecessors. And though I have a uniform sequence generated, the sequence itself is small in size. If I divide the complete circle into 4 quarter segments, then surely in every quarter I have one number. So the first quarter I have one number, say 1. In the next quarter it is 5. In the third quarter it is 9. And in the fourth quarter it is 13. Okay. So there is uniformity surely. But if I break down that into 8 segments, that uniformity goes. Say instead of 4 segments in the circle, so instead of here 1, 5, 9, 13. So if I have broken this down into 4 segments like this, in every quarter I have one random number generator, uniform distribution. But the same thing, if I break it down into 8 segments, then in one quarter segment there will be a number, in another there is no number. That uniformity will be lost. Okay, just remember. And usually there are 2 separate issues which we have to consider. One is, remember, all computers have a finite precision value and beyond which they usually round off. So there is always a round off error in systems. They can calculate the precision up to some decimal point, after which they will round off the values. So whenever we do a floating point divide operation or anything, you see that round off error will surely occur. And the other issue is the interaction of the sequence of random numbers with the application. So depending on what application you are going to use it for, there will be some kind of interaction of the sequence generated with the applications. So it particularly becomes a problem when the application requires many n-tuples of random numbers instead of just one random number at a time. So if the application needs to use 4 random numbers or 8 random numbers, the LCG which we use now cannot be used. Okay. So there is another example LCG, say LCG 50371. So if I use the same thing which we considered before, but with 37 as the modulo value, you see the random numbers which we are going to get in that sequence. So instead of mod 16, if I do mod 37, a small change, that's all. So here xn becomes equal to what? 5 into xn minus 1 plus 0 mod 37. When I used mod 16, I got only 4 points along the circle. But when I do a mod 37, you see the change. I'll be getting numbers 1, 5, 25, 14. I'll get all random numbers which is of length 36. So I'll get 37 different residues or 36 different residues when I do this. Okay. 0 cannot be used here because it will map to itself. That means if I have xn minus 1 as 0, then I'll have 5 into 0 plus 0. The next number I can't generate. It will always remain a 0. So I can't start with xn minus 1 as 0. So 0 is the only prohibited case in this. But if I leave out 0, I'm generating all other random residues less than 37. So I'm going to generate 36 random residues in this case, leaving out just one, that is 0, because if I have 0, it will map to itself. Okay. So this is still almost close to a maximal period generator because it's going to generate a random number sequence which is of length m minus 1. Instead of length m, I'm having the length of the random number sequence as m minus 1, which is 37 minus 1 or 36 in this. So what we mean to say here is, we call such generators as multiplicative generators. You see, because there is no increment value. In this linear equation which we have considered, when I have only the multiplier and no increment value, we call this as multiplicative generators. And these multiplicative generators don't generate proper random sequences if you don't choose this modulo value correctly. Only when you choose a proper modulo value, it will be able to generate high length random numbers or a high time period random number generator. So we have to learn something known as overflow and negative numbers before we proceed with this. So what do you mean by overflow? A large value of A is desirable to prove sufficient randomness. So that multiplier should usually be large and the modulo value should also be large to keep the period long. Whenever I have to keep the period long and I have to get a maximal length generator, both A and M should be large. Okay. So suppose we are working on 32-bit computers, or today we are generally using 64-bit or 128-bit computers. And if I'm using a 32-bit computer as an example you consider, A and M will generally be 31 bits long because the MSB is used to indicate the sign, right? So usually the numbers, how do we store on computers? The MSB will always be the sign bit. The remaining 31 bits will give you the magnitude. So usually it is in sign magnitude form, correct? So out of 32 bits, I'll have this as the sign bit, the 31st bit or the 32nd if I call, the remaining 31 bits will give you the magnitude. Okay. Now, what happens when I multiply two such integers of 32-bit in length? So you have two integers which are 32-bit in length. Will you get the result or the product within 32 bits?
No.
That depends on the value of the number. Usually there will be an overflow. So whenever I multiply two 32-bit numbers, usually you do it in programming labs everywhere. You store it in a double-sized integer, right? So if you use the actual size as single integer, the product will be a double, or if I have 32 bits, I'll give the storage space as 64 bits. So this is known as overflow. And fortunately, floating point multipliers or emulators which use floating point multipliers are designed to throw off the most significant bits. Okay, they'll retain only the least significant 32 bits, and the overflow which has occurred, they'll generally throw off most of the floating point multipliers. But if the result of multiplication is to retain that overflow which has occurred into the 32nd or 33rd bit, then the computer will treat that number as a negative number. So because there is an overflow into the MSB and the MSB has been set, computer would treat it as a negative number. Therefore, what we normally try to do, how to overcome this, is by masking the most significant bit. So we don't consider the sign bit, we'll just mask the most significant bit. And how do you do the masking? AND operation. You can say I mask and you can just do an AND operation, just mask the most significant bit and retain only the remaining magnitude bits. And this is how that overflow can be avoided. I think we'll stop with this here.